So in this video, we are going to see how basic operational changes can improve the energy efficiency for a standalone distillation column. There are various ways we can, save energy, but most of this, points are very simple to implement, and they don't require, you know, uh, either they don't require any additional financial implications, or if even if they require, they are very moderate in nature. So saving energy would be really beneficial in terms of the operation of distillation systems. So the first and foremost, as I think I also narrated in one of the earlier videos, that you can exchange heat between hot products and the cold feed. So your feed which is entering in the distillation column can exchange the energy between the energy with the products which are leaving the distillation system. Next is you can provide effective insulation. So insulations which are there may not be properly uh, you know saving the energy. They are not providing the required insulation to the distillation column, which will result in energy loss, and that will be ultimately will have to supply more than the required amount of energy. Then you can exchange heat at various trays. Now this serves two purposes. One, as I told you earlier as well, that there is, we supply at a higher temperature the energy and remove at a lower temperature. So this creates a work of separation. If we supply energy at various stages, your process will move towards a reversible process, and hence it will be more energy efficient. So this is one. Second is, if we supply energy at a various trays, right, we can supply a utility which is of a lower cost. So if I supply energy at the last tray, the temperature required to supply that energy would be high, but if I supply it at some 4 or 5 tray above that, naturally the temperature required of the utility will be less. So if I can supply energy at various trays, it will convert the process into a reversible process. As against that, it will also, like, if on plus it will also uh, give me ease of providing a utility which is bit cheaper. However, there can be a limit. There should be a limit of doing this, right? Because we cannot have exchanger at every tray. So hardly one or two additional such exchangers you can add. But if that is going to be beneficial in terms of utility cost, we should think of doing it. Another aspect is product purity and reflux ratio, which I think we'll see as we proceed further. We can also handle with column pressure. That also we can see. We'll see in the some of the slides as we move. Thermal state of the feed. If your feed is saturated vapor, right, then we require different amount of energy. Then we have a saturated liquid. So if your Q is 1, you require more heat, and if your Q is 0, the heat which is there can be used in the reboiler. So this the feed state can also narrate what you need to do as far as the energy supply is concerned. Feed state location can vary depending upon the thermal state of the feed as well as from the composition of the feed, and we'll see that how to tackle feed state location thing as we like. This is something which we have to, composition of the feed and feed stage are also interconnected, so we'll see that in the upcoming slides. And naturally, if required, we can improve the column internals. That also will be separately discussed. So let's start with product purity and the reflux ratio. So see, we have to check whether product purity, which we are going to supply to the our buyers, whether it is a soft constraint or a rigid constraint. That means, say for example, the requirement is 95%. So that 95% is a rigid constraint. Sometimes what happens is we try to provide over specified products. So 95 is required, we say 96. So 96 is a rigid constraint, right? You don't need 96, you need 95. So if you provide excess purity, how does excess purity comes for a given designed column? So for an excess purity, right, for a given set of number of stages and for all other conditions remaining same, you can only get excess purity by providing excess reflux. And if you provide excess reflux means more reboiler duty, and more reboiler duty means more condenser duty, and hence more operating cost. So if I go the other way around, that if I want to reduce the operating cost, I can reduce the reboiler duty. That can be reduced by reducing excess reflux, and that can be reduced by reducing excess purity. So if whatever is demanded, 95%, provide 95%. Don't go beyond 95%. So it is like, when you make a quality check, it's not only under specified product only to be watch for. Say for example, if you are providing an over specified product, that is 95% is required, you are supplying 96%, put a check on reflux ratio. It will save energy, right? So this is something which you have to learn, and you have to teach to the operator as well, so that he can also make sure that there is no excess purity going, because excess purity means excess operating cost, and you just need to educate someone. There is no additional investment. So that is why there are most of the operational improvements will not involve major portion as far as investment is concerned. Then comes your seasonal operating pressure. So we know that changes in pressure impacts the separation. If I decrease the pressure, my VLE diagram will make it easy separation. So VLE would be favoring the separation. So lesser the pressure, easier is the separation. More the pressure, difficult will be the separation. Now, if I decrease the pressure, what will happen is, as I decrease the pressure, the boiling points will also decrease. Now, decreasing boiling point means what? My reboiler boiling point also decreases, so reboiler temperature decreases, but at the same time, condenser temperature also decreases. Now, condenser temperature decrease means what? I have to supply a utility at a lower temperature. Now, say for example, if you are at a place where there is a huge temperature difference, right? In that case, what will happen? That the temperature of the cooling water will also change. Naturally, not as much as the other outside conditions, but cooling water temperature can also show you some amount of some degree of freedom. So, like in summer, if it is available to you in terms of degrees Celsius, say for example, if it is available to you at 35, 36 Celsius, if in winter it goes down to 27, 28 degrees Celsius, then this 8-degree change you can utilize. That means what? It can condense vapor which are still cooler compared to 35, 36. So this 8 to 10 degree you can utilize. So decrease the pressure of the column, let the temperature of the condenser go down, but by decreasing the column pressure, what happens is that your VLE will be favoring the separation, the required reflex ratio will go down because the number of stages are fixed. So if the number of stages are fixed, decreasing pressure will naturally directly impact your reflex ratio, which will again go down, and this will lead to the less amount of reboiler and condenser duty. So low temperature of cooling water will facilitate you to lower the operating pressure, and this can be used when temperature in winter is significantly down. So naturally, the temperature difference between winter and summer, if you want to implement this, the temperature difference must be sizable, right? Again, there is no investment. However, one thing is to be kept in mind, and that is that if your column is running at atmospheric pressure, there is no point making it below or sub-atmospheric, because if you want to make it sub-atmospheric, there is an investment. So naturally, this is not a good idea for columns operating under already operating under vacuum. Correct. Now feed plate location. Now feed plate location is generally decided based on the feed composition and feed thermal state. So we expect, like while we design a distillation column, we design it for one specific feed composition. However, because of some upstream processes, it is quite possible that your feed composition may vary. And if it varies, you need to take care of that, because what we expect is uh, in a distillation column, wherever the feed enters, we want temperature, pressure, and composition of that feed, it should be very much similar to the tray on which it is entering, so that it doesn't disturb the equilibrium of the column. So in order to maintain that, what we do is we can provide multiple feed points in the distillation column, which can vary the variation in the feed composition as well as its thermal state. So there might be, say, there might be 2-3 different feed points Like, this is your distillation column. Just a minute. This is a distillation column. This is your actual feed, like single design feed. But let's say the composition may vary. So you can provide two additional feed locations, and there could be a valve, the valve which can be operated depending upon the feed composition. So when these two valves are closed, your regular feed is going in here. If the composition varies, you can close these two valves and this may open and the feed may enter here. So likewise, you can provide multiple feed points, right? And that way you can take care of uh, variations in feed composition. Preheated feed streams also reduces the energy load on the column, which I think we already discussed, so I don't think that needs to be discussed. It is written no investment. However, no investment once the plant is already erected. Very slight investment in terms of providing additional piping for and valve for the feed. Composition of the feed. If the feed composition is having very high amount of light key, then it is always advisable to have an absorber before the main column so that you remove all the light keys before the main column. And if there is more heavy key, then add a stripper. Now this will have multiple effects on the column. One, the load on the column will decrease. Two, the temperature variation and the concentration variation within the column will decrease, which will ultimately improve the efficiency. But then, since you are going to put up one column here or one column here, like before the main column, naturally investment would be slightly added. Upgrading column internals. So most of the times we see that our column internals are worn out, and one of the easiest way to find that out is the pressure drop across the column. But what generally happens is that when the column internals are wearing out, it directly impacts the performance of the column. So generally what we do is that as the performance goes down, that means what, the purity will go down, and to check, to maintain the purity, we increase the reflux ratio, and we know that increasing reflux ratio is nothing but increasing the operating cost through the energy cost. So how do we know that whether our column internals are working or not? So for that we need to check about our actual reflux ratio and the design reflex ratio. If the actual reflex ratio is deviating too much from the design reflex ratio, we need to think on this. And that is, this is the rough guideline, that if the ratio of actual to design reflex ratio is greater than 1.3, you have a very good chance of savings by changing intervals. If it is between 1.1 to 1.3 this ratio, then you need to study, but still there are chances that your column internals are worn out. But if this ratio is less than 1.1, that is your design ratio and actual reflex ratio are more or less same, then there is something else. So you need to change and replace those internals, which may lead to some moderate investment. You can also improve the efficiency by changing the type of tray, right, or changing the tray spacing. So all these things can be done while the plant is in shutdown mode, and that it attracts some amount of investment. Rest you can do with the help of heat integration, and that is by adding pinch analysis or having upgraded control system. So both of them requires higher amount of investment. Control system, naturally you go with a proper control, no manual things come into the picture, so the set points are being met and hence your energy would be saved. So we'll discuss more on heat integration or pinch analysis in our upcoming videos. So this particular video we tried to discuss how some basic operational improvements can be done to save energy of a standalone column. Thank you.